In this lecture, we will try to derive the continuity equation. Continuity equation is basically the conservation of mass equation. First, we will consider the one-dimensional pipe flow. So this is the pipe, and we are considering a small area here with a dimension of delta x, and its cross-sectional area is cap A. Here you can see the flow across this small area. So what is the volume of liquid flowing across this area? That is equal to capital area into delta x. That is cross-sectional area into delta x. That means across this control volume. And how will you calculate the discharge or the flow rate per second? We will divide the volume by time, that is equal to A into delta x by t, and which is equal to area into V, because delta x by delta t is equal to velocity. This V is the velocity, area into velocity. So discharge is equal to area into velocity, that is flow rate. Usually the unit is meter cube per second. So how will you find the mass flow rate? This m dot means kilogram per second. What is the mass flowing through that? So mass flowing through this is equal to rho into discharge, or rho into volume flow rate. Rho is the density. So discharge is also equal to A into V. So m dot is equal to rho into A into V. That is the mass flow rate across this control volume. Now we will consider two sections, 1 and 2, in the pipe. So what is the mass flow rate across this section 1? It is equal to m1 dot, that is equal to rho 1 a1 v1. Rho is density, area is the cross-section at 1, cross-sectional area at 1, and v is the velocity at 1. And what is the mass flow rate across 2? That is equal to m2 dot, that is equal to rho 2 a2 into v2. Density into cross-sectional area into velocity at 2. So according to law of conservation of mass, whatever mass is entering at section 1 should leave at section 2 if there is no mass stored inside here. So if m1 dot is equal to m2 dot if there is no mass stored inside this pipe. So that is the conservation of equation, that is m1 dot is equal to m2 dot, which is equal to rho 1 a1 v1 is equal to rho 2 a2 v2. So for any section across the pipe, rho into a into v will be constant. And this is the continuity equation in one dimension. That is, density into area of cross section into velocity will be equal to a constant. Now we will try to derive continuity equation in two dimensions. So here we are considering a small control volume of dimension delta x and delta y, and also in the z direction, or the depth of this control volume is taken as unity, that is 1. Instead of delta z, we will take 1. So there is a mass flow rate m dot x flowing in the x direction, and at x plus delta x, the mass flow rate is m dot x plus delta x. So initially this position was x, so this position will be x plus delta x. Similarly, m dot y, that is a mass flow in the y direction entering here, and m dot y plus delta y leaving here, m dot y and m dot y plus delta y, because at this initial it will be y position and here it is y plus delta y. Now what is m dot x plus delta x? This is equal to m dot x plus dm dot x by dx into delta x. This is the rate of change of mass with respect to x. So that rate of change of mass into delta x will give you the change in mass flow rate across delta x. So this will be equal to m dot x plus delta x will be equal to m dot x plus dm dot x by dx into delta x. You can write this for almost all variables, that is ux plus delta x is equal to ux plus dux by dx into delta x, like this. And similarly, m dot y plus delta y is equal to m dot y plus dm dot y by dy into delta y, just like the earlier case. Now let us apply the conservation of mass equation. According to law of conservation of mass, whatever mass entering here and whatever mass leaving out here, the difference between these two will be equal to the rate of change of mass inside this control volume with respect to time. Suppose 5 kilogram per second is entering here and here it is leaving 4 kilogram per second. So that means 1 kilogram per second is stored inside here. Okay, that is what do you mean by law of conservation of mass. So m dot x, what is m dot x? How will you find m dot x? Just like the earlier case, we have derived the continuity equation in one dimension. So here we are taking only x dimension. So that is formula is, we have found it to be rho a v. We are applying this equation. This v, velocity is the u and density is rho and area is the cross sectional area here, that is equal to delta y into 1. That is the cross sectional area. Similarly, m dot y is equal to rho into delta x into 1 into v. That is the velocity in the upward direction. Delta x is the cross sectional area in the y direction. Rho is the density. So you can write m dot in minus m dot out. So what is m dot in? That is equal to m dot x minus m dot x plus delta x plus m dot y minus m dot y plus delta y. That is total mass entering minus total mass leaving. So now we can write m dot in minus m dot out is equal to, see what is m dot x minus m dot x plus delta x. We look at these two equations. See, we will substitute m dot x here, x plus delta x, that is equal to m dot x plus dm dot x by dx into delta x. So it will become minus dm dot x by dx into delta x. Similarly, if you substitute m dot y plus delta y here from this equation, you will get m dot y plus dm dot y by dy into delta y. So this will be these two. Okay. Now we will substitute del m dot x and m dot y from these two equations. So m dot x is equal to rho into delta y into 1 into u, and m dot y is equal to rho into delta x into v. If we substitute these two, we will get an equation like this. That is m dot in minus m dot out. So we will write that equation once more. That is m dot in minus m dot out is equal to minus d rho delta y u by dx into delta x plus minus d rho delta x v by dy into delta y. So you can take out delta y and delta x out, because delta y does not depend upon x. It is a constant. Similarly, here you can take delta x out. Now, what is dm dot cv by dt? That is m dot cv. That is the control volume. Mass flow rate is no dot. This mcv is the mass inside the control volume. So mass inside control volume is equal to rho into velocity. Rho into volume of the control volume. So volume of the control volume is equal to delta x into delta y into 1. There is also 1. So we are not taking that here. So delta x into delta y. So that is equal to d rho by dt into delta x into delta y. So you will get m dot in minus m dot out is equal to dmcv by dt. That is the law of conservation of mass. So if we substitute from the earlier equations, minus d rho u by dx delta x delta e, that is m dot in we have derived earlier, and m dot out is equal to minus d rho v by dy into delta x into delta y. This is equal to d rho by dt into delta x by delta y. So we can cancel out delta x delta y from LHS and RHS. So you will get this equation, minus d rho u by dx plus minus d rho v by dy is equal to d rho by dt. So this is the continuity equation in 2 dimensions. This is the continuity equation in 2 dimensions. Here we can make some modification. For an incompressible fluid, rho will be constant. So that means this equation d rho by dt will become 0, and here rho can be taken outside because it does not depend upon x and y if it is constant. So you will get rho into du by dx plus rho into dv by dy will be equal to 0. So that means du by dx plus dv by dy is equal to 0. So this is the continuity equation for an incompressible fluid. For an incompressible fluid. So if you are taking water, it is almost incompressible. You can apply this equation. And for a 3 dimension, you can extend this equation to a 3 dimension. For a 3 dimension, general continuity equation will become d rho by dt plus d into rho u by dx plus d by dy rho v plus d by dz of rho w. This will be equal to 0. This is the general continuity equation for 3 dimension. In this case, we are taking another dimension, that is delta z. Instead of 1, we are taking delta z.